Where we left off is, I derived the kind of complex block band structure for EIT. So the complex wave vector k as a function of frequency or detuning. And what we concluded is that EIT gives you a very slow group velocity, which you can tune via the control field intensity. And that the bandwidth of EIT is also finite. Okay, so exactly on resonance, you have perfect transparency, but the moment you go off, you start to absorb a little bit of that light. So now let me explain to you more how to use EIT specifically for quantum memory. And the key idea is simply the following. So I have a photon coming in. Photon weak coherent state doesn't really matter. And I have this kind of atomic medium of length L, okay? And the goal is, if I really want to use the atoms as a hard drive, it's clear that this photon has to at least fit within the atomic medium. Right, so if my atomic medium was 1 centimeter long, but my photon is so long, if it's a plane wave, it's infinite in length. Okay, so it doesn't even fit within the atomic medium. Then of course, it doesn't work as a hard drive, right? So what I really need is that I need the photon, once it's inside the medium, to completely fit inside. Okay, so I need my photon. Must fit inside the ensemble. Which means the maximum length it can have inside the medium is given by the length of the medium itself. Okay? So what that means is that now I can think of its spatial Fourier components, and that places a bound on the range of Fourier components. Okay, so my minimum bandwidth in wave vector space has to be on the order of 1 over L. So if the bandwidth in K space is smaller than my pulse is too long. Okay. And so, right, the fact that the photon must fit inside leads to this condition that delta K has to be on the order of 1 over L. And once I know the kind of range of K vectors I need, I can plug it into my dispersion relation here to translate it into a range of frequency components. So using the fact that there's a well-defined relationship between K and frequency, now I can figure out the frequency bandwidth of that pulse, in order that it fits inside. So it turns out that so if you do that calculation, then what you find is that this kind of characteristic bandwidth, the minimum frequency bandwidth that you need to satisfy this condition, is given by omega c squared divided by gamma 1d times n. And now, once I know my kind of frequency bandwidth, I can plug it into this formula for absorption. Okay, so if I take that particular frequency and plug it into absorption, now I figure out roughly how much that photon gets lost as it tries to propagate through. Okay, so the characteristic kind of loss is given by 1 minus t of this kind of characteristic frequency here, squared. And then if you go through the math, that's given by, or proportional to 1 over the optical depth of the medium. Okay? So remember that this optical depth was something I previously defined to be proportional to the atom number times the coupling efficiency of a single atom to the Gaussian beam. Okay? So this is a kind of concrete example of this claim I made earlier that anytime you try to do anything coherent with atomic ensemble, the optical depth is going to enter in as the error at the end of the day. Okay, so in this context here, what error means is I try to send in a photon, coherently do EIT to get it into to compress it into the medium, but then with a probability proportional to 1 over d, the photons managed to scatter into 4 pi, and I lost it. Okay. And again, in realistic experiments, so this is a kind of fundamental bound on the error. Of course, in realistic experiments, the number of atoms is not really a limited resource, so you can try to keep cranking up the number of atoms. But at some point, you hit like kind of technical complications with working with so many atoms. So the best for the best optical depths that people can actually reach in the lab and still maintain a kind of functional experiment, this error for single photon qubits for quantum memories is still around 10 or 15%. Okay. So it's still not a quantum memory yet, because what I've kind of convinced you of so far is that you come in with a photon, it enters this atomic medium, it starts to propagate very slowly. And if I want to kind of take that photon and make sure that it fits completely inside the medium, then this is the error at which I can do that. Okay? But quantum memory is a little bit more, because quantum memory, the idea is that okay, if I don't do anything else, then I know this pulse is propagating at a slow group velocity, but then it's just going to come out at some predetermined time. And the idea of having a quantum hard drive is that I like this pulse to actually stay there for an arbitrary amount of time that I want, and then when you tell me, then I give you back the photon. Okay, so we need to do a little bit more to actually turn this thing into a quantum memory. Yep. No, that's a great. I mean, that's the essence of EIT. So maybe I think what I'm going to say in the next 10 minutes will answer that question online. But if not, then you can maybe come back and ask the question again, or ask it another way. Okay. So now let's kind of ask a somewhat deeper question, which is, here I was just trying to kind of draw abstract cartoons, but let's actually think more deeply. What does the pulse actually look like? So just to make it concrete, let's start with a photon whose length outside of the medium is given by L out. Okay, so we know it enters into our system of atoms. And sorry, when I draw this pulse, we can. There's nothing kind of quantum in this argument. So if you want, you could just say, even if I had a kind of classical pulse, and I know the electric field amplitude E of R and T. So you can think of this as a snapshot at a particular point in time. Now the question is, when it's inside, if I were to take another snapshot at T prime, what does the electric field amplitude look like? So let's just try to guess the answer by pointing out some things that are true. So the first thing is, remember that we're sending in pulses around delta equals 0. Okay, so when delta is exactly 0, all these terms drop out, And then my dispersion relation inside the medium is exactly k equals omega over c. Okay, so that's exactly the dispersion relation of light in empty space, which means that my refractive index, my phase velocity, is exactly that of vacuum. Or that's to say that, so on one hand, I know that my phase refractive index is equal to 1. So if I pass from one medium, which has a phase index of 1, to another medium, which has exactly the same phase index, all my boundary conditions for the field should be continuous, right? Which means that, so imagine that this was my kind of pulse outside, and I have a maximum, amplitude of electric fields. The fact that my index is 1 implies that the maximum field amplitude is preserved. Right? Because at the boundary, I should maintain continuous values of the electric field. Okay? So I don't know what my pulse shape is a priori, but I know the peak value of that has to be the same as the peak value from outside. At the same time, I can look at the group velocity, and I know that the group velocity inside, compared to the group velocity outside, which is just the speed of light, I know realistically that that's much smaller than 1. Okay. And so anytime I go from a fast propagating system to a slow one, to maintain kind of linearity of the system, I know that my pulse has to compress. Okay, so the fact that I go into a much slower medium means that my pulse length inside, let's call this L in, I have to have that L in over L out equals Vg over C. Okay, so just to summarize, I start with the pulse outside. When it enters, the spatial extent of it really compresses by a lot, but the peak amplitude stays the same. And now let's think about electromagnetic energy. Okay. So if the peak amplitude is the same, but then my width is much smaller, then if I just calculate my total electromagnetic energy density, so E squared, integrated over all of space, and then I should get that the ratio of U in, so the total electromagnetic energy inside versus outside, also has to be the group velocity divided by speed of light. So it seems like I'm losing energy, right? Because my pulse here is way smaller than it was outside. At the same time, though, I can't really be losing it incoherently, because I know when this thing propagates, I have EIT. So as long as I maintain a proper bandwidth, this pulse, when it comes back out, will actually come out with the same energy that I sent in, almost, up to this kind of factor of loss here, which means that this kind of loss of energy can't just be real absorption, but the energy has to be coherently going somewhere else. So the amount of electromagnetic energy reduces, so reduced. But at the same time, we know it can't be lost. Okay, so if it's going somewhere, then there's only kind of one possibility. So I drew this kind of 3-level structure before, where I have my input fields, my ground state, my excited state, my state S, and a control field. I know it's not an excited state because I argued that that's why the system is transparent in the first place. I have no excited state population. So what's the only degree of freedom left over? It had to have been transferred to a spin excitation S. Okay, so this what I call a photon, very roughly speaking, actually when it's inside the medium is actually very little photon. It's effectively gotten turned into a spin excitation in my state S. Okay, so that's the only kind of consistent argument that you can make. So I made this kind of argument based on just, process of elimination or lucky guessing, but it turns out if you do the full calculation, that's exactly what you find. So, so from that you conclude that the energy must be going to a state S. If you want to cast out a little bit more kind of fancy language, you would say that the eigenstate inside my atomic medium are actually polaritons. Polariton is just a fancy name in physics for any type of hybrid excitation. Okay, so you get a polariton. Which is roughly, so you can define some abstract mixing angle theta, which is part photon. Plus cosine theta and a spin excitation S. And I write this as a kind of symbolic Hilbert space. So I have n atoms, so the spin excitation S could be sitting on any one of those n atoms. This is just meant to represent that total space. And then, if you believe in this set of arguments, you would conclude that this kind of ratio of population in the spin versus that of the photon is exactly C over Vg. Yep. Yeah, it's because omega C enters kind of everywhere. So, so on one hand, omega C dictates the amount of compression. So that should dictate, how much, I need to. That should dictate, delta K. But then you see that omega C also enters in the absorption. So it's just you can think of it as it's a global like rescaling, if you want, of my EIT properties. Yeah. Okay. So I didn't, this I just leave as a claim, but it's actually pretty easy to go back into these equations and show that it's true. In particular, I erased it now, but earlier I did, give you the formula for the excited state population as a function of detuning. And if you were to go back and reevaluate how much population is sitting there versus how much photon number I actually have, you would exactly confirm this result here. Okay, so now let's actually talk about the quantum memory. So let me tell you kind of the mathematical statement, and then my claim is actually it doesn't really matter. Okay. So the idea for a memory is to use a time-dependent control field omega C of t. Okay. So let's just be kind of naive and guess what might occur. So as long as I tune omega of c in a way that's adiabatic, roughly speaking, then you imagine that this kind of group velocity formula still holds, except now that I put my so same as my group velocity depends on my control field intensity, and then if I play with my control field intensity as a function of time, I can actually turn omega c to 0, and in the same time turn the group velocity to 0. Okay, so I can turn omega of c down to 0, and that implies that my group velocity is 0, so my pulse has literally stopped inside the atomic medium. Okay, so now you have this notion that's a stationary hard drive. Well, what the heck is going on? Is it a photon? Is it literally that I took a photon and I turned its speed to 0? Well, no, because of this argument here that the real, once it's inside the medium, it's actually a polariton. Okay, so the mixing angle, or sorry, let me say. So the population, so if I do that, then the population in the photon versus the population in my spin state S, that also goes like Vg over C. So this thing is also going to 0 at the same time. So basically what's happening is that this polariton is gradually getting slower and slower because it's turning more and more into a pure spin excitation. Okay? And it's completely, everything here is completely unitary. So once it's completely spin, at some later time, I can undo the process. I can turn back on my control field. It'll get remapped to a polariton that's now partially photon and start propagating out of the medium. Okay? So in principle, for this to be true, you have to set some conditions on adiabaticity and so on. So mathematically, that's true. In practice, it doesn't really matter because any reasonable group velocity, so in practice, Vg over C is always very, very small. So the second you do EIT and you're inside, in practice, your polariton is already 99.9999% spin excitation. So even if you just chopped off even if you just instantly turn this control field to 0, at worst you've lost kind of some small fraction of that polariton in the process. Okay. So that really completes the story of how a quantum memory works. It works on one hand because you can convert your photon into a polariton with very high efficiency, so with a loss that scales like 1 over optical depth. And once it's this polariton, that's some mixing of photon and spin, you can use the control field to tune that mixing angle and turn it into a pure spin excitation. So you turn the group velocity of this pulse to 0, and there's no mystery because at that point it's no photon left in the story. Okay, so that I think completes the story of a quantum memory and EIT. Before we move on, are there any questions on this part? I mean, as an aside, I find this to be a beautiful problem, right? I mean, the physics or the mathematics is nothing complicated, but there's so much subtlety contained in understanding the consequences of group velocity versus phase velocity, et cetera. These ideas of polaritons, adiabaticity. Oh, to map it back into a photon? So the statement is that this kind of I didn't explicitly write out the polariton dynamics, but the point is it's totally unitary. So so maybe I'll leave it as a claim. So the claim is that your polariton, when you start playing with the control field as a function of time, obeys the following wave equation. Okay, so this is a purely coherent evolution. The only thing that you have is this time-dependent, group velocity. So you can speed it up, slow it down whenever you want. What's kind of left out here is this polariton itself has this mixing angle that's depending on Vg. But what this allows is if you tune Vg to 0, then the whole thing just stops. It's stationary. This is a pure spin excitation. But because it's purely unitary and coherent, you can then turn on the control field, turn this group velocity back up to a non-zero value, and eventually map your state into a pure photon leaving the medium.
One thing is not clear to me. Like, I mean, I would expect that this turn off, turn on should be somehow synchronized with the, like the wave packet is coming, and so I have to turn on at a specific times. But here it looks to me that this kind of that you have to match when the photon is entering is missing.
Oh yeah. So that's an important point. So you can play. You can turn this control field down to 0 in almost arbitrary sense, provided that your pulse is already completely inside. So if your pulse is partly inside and partly outside, and then you try to play with the control field, then you'll really distort your pulse, right? Because your polariton on the outside is pure photon, so it doesn't care about your control field. And then, yeah, so this is all true, provided that your pulse gets localized or gets compressed in your medium completely in the first place. And then you can play all these games with your control field.
But indeed, also this like eigenstates is a polariton, but does it imply, I mean, we are assuming that the system immediately relaxes to this eigenstate? I mean, is it a stationary, are we in a stationary state? Is it like?
Essentially, so, right. I mean, so again, I didn't prove it, but if I were to kind of write it out more properly, so maybe I can kind of sketch the idea. Like, so if I were to plot my dispersion relation, it's actually multi-value. So I have multiple bands. So there's one band here that you would call the EIT band, which is the one we focused on. So when I wrote this K of delta, there's really this one band in the middle. There's some other band up here, which I don't really know. It's a lossy polariton. And the point is, like, so once your medium is, once your pulse is inside, you know the degree of compression, or you know the spatial length. So that defines some range of K vectors that you're populating. So you're populating some region in this band dispersion. And now when I tune up and down omega over C, I maintain spatial periodicity. So my delta K can't change, provided that my pulse is completely inside, right? So when I play with my control fields, this range of delta K that I'm occupying is conserved. The only bad thing that can happen is, because I have a time-dependent Hamiltonian, it is possible that I can jump from one band to another. Okay, so that's the effect of non-adiabaticity. And so there is an adiabatic condition that you can mathematically calculate. I guess what I'm saying is, in practice, you're so much in this kind of spin state that even if it was completely diabatic, in practice, the whole thing experimentally would work just as well.
Thank you.
So the reason why people don't use it so much in experiments, right, is like, just to summarize, is like because this loss is large, because like it's limited by this optical depth, which is
Right.
which is, well, not like well, it's not a large number, so so the losses will be still high, and we'll lose like quite a like high percent of the original quantum information, which
Right.
makes it like not helpful, right?
Well, so people still use I mean, I think there's a fairly large set of experiments which use EIT and quantum memory of some form or other. So of course, even if it, right, at the end of course, if you want like full-blown quantum computers, you would like that number to be 99%. Even if it's 90%, there's still certain applications that you might want to try out. So yeah, right. So the number isn't as good as we would like, obviously, but it doesn't necessarily stop people from trying to do these experiments and try to do something with the amount of error that they have.
I see. Have people thought about like any error correction protocols within this framework? Because I can imagine even if like the loss is like, I don't know, maybe a few percent, the there might exist like some error correction protocols which can correct for this amount of errors.
Yeah, so that's a that's a really good point. I mean, right. I guess maybe the broader question is how do we decide what amount of loss is enough? That very much depends on your specific application. If we want to, as one example, so if you can do photon gates, then in principle you can build up these so-called cluster states of photons, which are just they have a special entanglement structure, and then it's kind of known that in principle with these cluster states you can do quantum computing. So there has been work on, okay, like if these cluster states are not perfect, if we have photon loss or the gates are not pure, what's the threshold to really reach fault tolerance? It's a balance that is always evolving because you can always try to find better things and so on. But I think there's, in principle, I'm not an expert, but I believe there's schemes where you can tolerate even around 10% of photon loss and still, in principle, be fault tolerant. You might require a massive amount of overhead of photons, and then there's a question of how do you store all those photons, et cetera. But yeah, in principle, like maybe even 10% loss could be tolerable within cluster state quantum computing.
And sorry, how would this toy model here like translate to cluster states? Like, how should I say think of those cluster states? Because I'm used to thinking about cluster states, but like in a spin context.
Yeah.
So like, would it be again like trying to pose certain structure to like those atoms we're having, and then like putting them in a cluster state, or it would be something about the photons?
Right. Yeah. So a priori, quantum memory has nothing to do with the cluster state. A cluster state is a particular state of entangled state of pseudo spin 1/2 systems or qubits, and then it's known that if you measure them in a certain way, you can do quantum computing. So at that level, right, that's a completely general statement. Quantum memories would, I think, potentially come in if So the idea is, most likely the number of photons in that cluster state to do something useful would be massive, right? And then you have to, do measurements, et cetera, also a massive amount. So I guess the point is that if the total time you need to do the computation is long enough, at some point, again, the photons can't live as pure photons beyond a certain amount of time, like in a fiber or free space. And so once the length of time of your computation becomes long enough, eventually you would need a place to store those photons until it was time for you to actually go and measure them. So that's where the quantum memory would come in. And then so then the question is, okay, now if I need a quantum memory and I put a photon in and out, what's that error? Or what's that loss probability? If that loss probability is too big, then that kills the cluster state in the first place. Okay. So a quantum memory is, again, one of the kind of most pursued experiments in terms of trying to use photons or create coherent atom-photon interfaces. As I said before, though, it's a completely passive operation. So the goal in the big picture is you give me a set of photon qubits to store. I'll keep them for you, and I'll just give it back to you later. Okay, so I'm not making your system, ideally, I'm not making your photons any worse or better than what you gave me in the first place. So then that raises the issue. Okay, like how if we so quantum memory, you presumably want to be storing quantum resources, entangled photons and so on. And then that leaves the question, how do you generate entangled photons in the first place, using these same atom-light interfaces? So that's going to be the next topic. So our goal will be to realize a photon-photon entangling gate. But first, we'll need a kind of brief digression into Rydberg atoms and Rydberg states. Okay, that's going to be the new resource we're going to add. To allow strong photon-photon interactions to be possible. So Marcello presented kind of already a brief introduction to Rydberg states yesterday. And let me just kind of recap the main points. So if you take any typical atom, you can even take hydrogen, but it's completely, these statements are quite generic. Remember that you have a set of, so your atomic states are labeled by some principal quantum number n. So n equals 1 would be the ground state. You could have n equals 2, 3, 4, etc. We discussed already that the kind of energy spacing of an atom is very anharmonic. So level n typically has an energy of 1 over n squared. So you have actually an infinite discrete set of Rydberg states. So up here you have kind of n equals infinity. And when n is very big, it means so when the energy approaches 0 from the negative direction, it means your electron is almost free, right? So these are kind of, so these states are bound, but they're kind of almost free electrons. And if you just go back to the kind of quantum mechanical wave functions, for large n, you just go back to hydrogen. What you find is that if you look at the kind of average distance of the electron from the origin, from the nucleus, this thing actually scales like n squared. Okay, so that just kind of quantifies my statement that these high-lying Rydberg states are almost free. Okay, so the electron starts to spend a lot of time very far from the nucleus. And it's a little bit of abusive language, but when you have an electron that's sitting very far from a nucleus, you can think of that object as having a very big dipole moment. Okay? So now when you have two atoms, both in Rydberg states, they see each other's dipoles very strongly, and you get a very large dipole interaction. Okay? So this state here has a large dipole. And therefore, when you have two atoms, you get a large dipole-dipole interaction. Which takes the following form. Marcello also mentioned this yesterday. You get an interaction that scales like the distance. So we have two atoms separated by a distance d. And if they're both in the Rydberg levels, you get this dispersive interaction where the energy level of one Rydberg is shifted by a large amount relative to its bare value. So the cartoon picture, if you want, is if we call this atom 1, so we could call this some hypothetical ground state. Here's a Rydberg level. So imagine I plant atom 1 in the Rydberg state. And now as a function of distance, so what I'm plotting on the vertical axis is energy. So if I look at atom 2, if atom 2 is very far away, then the Rydberg atoms don't see each other. So the energy of this Rydberg state is exactly the same as that of an isolated atom. But as I bring atom 2 closer and closer, I notice that this Rydberg level starts to shift in energy. So there's an effective interaction energy. Okay, and this curve here goes like 1 over d to the 6. Okay. So what you call Rydberg state or not is somehow arbitrary. So if you maybe remember from like high school or university chemistry, even two atoms in the ground state have this kind of 1 over d to the 6 attractive interaction. That's what you call van der Waals interaction between atoms or molecules. The main manifestation, though, that you're in a Rydberg state versus just the usual boring ground state is how this C6 coefficient scales. So C6 scales with this principal quantum number like n to the 11th power. So this van der Waals interaction for normal ground states, which is normally very weak, or where you need the atoms to be very close together before there's any effect, all of a sudden when you're up in the Rydberg state, these atoms can be relatively far away, even microns in distance, and still see this van der Waals interaction. Okay. So now let's illustrate how to use the van der Waals Rydberg interaction for quantum optics. So let me try to first just draw in cartoonish form how a photon-photon gate would work, and then I'll explain the steps in a little bit more detail. So main steps of the gate are the following. So let me kind of actually define the gate first. So we need to have some notion of two photonic qubits. Here I'm going to encode it actually in photon number rather than polarization. So in quantum computing, there's something known as a control phase gate, which is an entangling gate. And then the idea is the following. So I have two photon pulses, which I'll call A and B. And within each pulse, I can either have 0 photon or 1 photon. So that defines my qubit degree of freedom. And the idea of a controlled phase gate is that if I have 0, 0, it gets mapped to 0, 0. 0, 1 gets mapped to 0, 1. 1, 0 gets mapped to 1, 0. And then the non-trivial thing is 1, 1 gets mapped to minus 1, 1. So you can easily convince yourself that if you started with a product state of photons in A and B, and you applied this unitary map here, all of a sudden, in general, your new state would be non-separable or entangled. Okay. So how might you do that with photons? So in step 1, you do EIT on pulse A. So the idea is that we'll have the usual 3-level structure that I showed before. We'll have a ground state G. Pulse A will come in and talk to the G to E transition. And then we'll do EIT. So we need a long-lived state, a metastable state. But instead of using a kind of true ground state, like I showed before, we're actually going to try and map up to a Rydberg level. Okay. So the fact that you're trying to map to a higher energy state rather than lower, it doesn't change any of the equations or physics that I described before. And so the end product is that you come in with a photon A. If there was a photon, so let's say that this was one photon Fock state. Now in your atomic medium, you've created one Rydberg excitation. Now in step 2, we'll send in photon B. So, yep.
In that case, I already have a photon inside my atomic media, right?
Yes.
Okay.
Yeah. Right. So if there was if A had a photon, then there would already be a Rydberg excitation inside. And now we're going to send in pulse B. And now let me try to, actually, let me make this medium longer just so I can kind of properly draw the physics. So let's imagine that this Rydberg state was right in the middle. So now let's draw the kind of energies of my states as a function of position. So let's call this axis Z, right? So in other words, what I'm trying to do is I'm looking at different atoms at different spatial points inside the ensemble. And what I want to ask is, what are the energy levels as a function of position? So the ground state is totally uniform. Okay, so the ground state has the same energy regardless of where it's sitting in the ensemble. The same thing is true with the excited state, but the non-trivial physics is in this Rydberg level here. So again, the point is I already have one atom that's up in a Rydberg level. Now I want to look at another atom. If it's in a Rydberg level, I want to ask what is this resonance energy? And so the point is that the Rydberg interaction is relatively short range. So if I'm far enough from this existing Rydberg excitation, these two Rydberg atoms don't know about each other. Okay, so the energy of another Rydberg level would be unaltered from that of an isolated atom. But now, as I look at atoms closer and closer, eventually a Rydberg atom here does know about the existence of the other Rydberg atom through this Rydberg-Rydberg interaction. Okay? So at some point, the energies start to go up and really diverge. Okay? So this picture is really important. So does what I'm trying to draw or convey make sense? Okay. Yep. Yeah, so EIT, right, so EIT does not depend per se on whether your third state is kind of below the excited state or above the excited state. The only thing that you need is that third state you're using should be reasonably long-lived. Okay, so if that state also decays very quickly, then that's going to ruin EIT. But that's really the only constraint to make EIT work. Okay. And then the trick of step 2 is we're going to send in photon B, again under EIT conditions. So I'm going to try and send in photon B on the E to G transition. I'm going to have a control field that's going to be resonant with the E to R transition, but it's going to be resonant assuming that my Rydberg state is in the right energy. Okay. So the point is that when I'm very far away from the existing Rydberg, my EIT is going to work exactly the same as always. So this photon B doesn't know about this Rydberg. It starts to enter. It sees this reduced group velocity. It turns into a polariton, et cetera. But then you see that at some point, so the point is my control field frequency is fixed, right? I don't get to change it as a function of position. So at some point, when I get too close to the existing Rydberg, my control field effectively, so if this detuning becomes huge or infinite, all of a sudden this control field doesn't even see a state to couple to anymore. So in this region here, even though I have the third level and this control field, this third level is pushed off so far away that effectively it's not there. And so in this region here, this photon B does not see a 3-level EIT medium. Effectively, it only sees states G and E. It sees a 2-level medium. And it's nonlinear, and it's interacting, because this 2-level medium, or this 2-level region, only exists if I sent in a photon A in the first place. Okay. So it turns into a conditional interaction between photons A and B. And the practical consequence, if we just talk about kind of pure optics, is I derived the dispersion relation of EIT. I also derived for you the dispersion relation of a 2-level medium, and they're completely different. So what you can say, roughly speaking, is that this existing Rydberg excitation, or this photon A, changes the refractive index of the atoms in a macroscopic region. And then so when photon B passes it, it can try to pick up an extra phase shift in the process. So that's the kind of qualitative idea of the photon-photon gate. Okay.
Like this 1D chiral waveguide right now, right? And
it's not so it's not guaranteed to be pi. You have to fine-tune it.
Okay.
So you have to choose the detunings, the Rydberg blockade region, et cetera, to really give you a pi phase shift. So I'll discuss that in a little bit.
Perfect. Thanks.
So So there are more sophisticated schemes where, like, this pi phase shift can actually be kind of robust, but that's not. I mean, so I think it's kind of conceptually clear that Rydberg interactions are a very nice resource to implement a photon-photon interaction. But you can imagine, if you think about it hard enough, you could probably cook up any number of ways to use the Rydberg interaction. So here I'm just giving one particular example, but there's more sophisticated ways to use the Rydberg, and for example, try to make a pi phase really robust. But I won't mention it explicitly. So just to summarize how the gate works, if A had a photon, then B sees a different refractive index. When it tries to propagate through. Due to the 2-level medium that was effectively induced. So let me try to draw the same picture again. So I have my Rydberg excitation coming from A. And I have some spatial region where, so outside of this spatial region, from the standpoint of photon B, it looks like I have EIT. And then within this spatial region, instead, it looks like I have a medium of two-level atoms. Okay? And this, you can define this distance to be 2 times RB, where RB is a so-called blockade radius. It's the size of the region whose refractive index was changed. Yep. Oh, sorry. So here I'm encoding my qubit in photon number. So pulse A can either have 1 photon or 0. Yeah. Okay, so another kind of figure of merit you can define is the optical depth, not of the entire system, but just of this kind of blockade region. Okay, so you can define a blockaded depth. dB, which looks the same as the formula that I showed you before. So before I defined the optical depth as the number of atoms times the coupling efficiency to the Gaussian mode. Now here, instead of the total atom number, I'm only going to include the photon number or the atom number within this blockade region. So this is 4 times the density of atoms times 2 times the blockade radius times gamma 1D over gamma. Okay, so now we just have to understand exactly how we're going to use this 2-level medium to pick up an extra pi phase shift in propagation. And here we can recall our previous results for a 2-level atom. So remember that before I showed you this plot of so as a function of detuning, I plotted t squared. Okay, so in a 2-level medium, or a single atom in a 2-level medium, it's going to attenuate light on resonance by amount that's proportional to gamma 1D over gamma. And then recall that when I'm far away from resonance, the amount of attenuation scales like gamma 1D over detuning squared. And then I also plotted out for a single atom, a single 2-level atom, the phase shift as I propagate through. Okay, so the maximum phase shift you can pick up is also proportional to gamma 1D over gamma. And then in the tails, when I go to very large detuning, that phase shift scales like gamma 1D over detuning. Okay? So again, the main message is if I'm not sitting on my resonance of a two-level system by sitting very far away, of course, the amount of phase shift I can pick up gets reduced because my atom can't respond as effectively to non-resonant light. But then my absorption drops down even faster. So then the strategy, if I want that my photon B picks up an extra pi phase shifts here, is I send in photon B off resonance. Okay. So when it's off resonance, then for every atom it passes in this blockade region, it picks up a phase shift of gamma 1D over delta. It's not going to be perfect because there's some chance, gamma 1D over delta squared, that photon is going to disappear, but I'm relying on the fact that my good stuff is better than my bad. Okay. So the idea is to send a photon B off resonance. And then you can see that the detuning I should choose becomes constrained. Okay, so if I want to pick up a pi phase shift, what I need is that the phase shift per atom times the number of atoms in the blockade radius equals pi. Okay. So that was the kind of fine-tuning that I mentioned earlier. If you know the size of the blockade radius or you know the number of atoms, you need to choose the detuning of your photon B to guarantee that the phase shift they accumulate is pi. Okay, so this fixes the detuning. And then once you know the detuning, you can go calculate the absorption. Okay. So then the loss is approximately given by gamma 1D over delta squared times number of atoms. You know what the number of atoms, the relationship between the number of atoms and the detuning is. And then if you work it out with all the kind of factors of 2 and pi put in, it's 16 times pi squared divided by the optical depth per blockade region. Okay. So again, you see that the kind of optical depth, in this case not of the entire medium, but just of the blockade region, enters in as a fundamental limit of how well you can execute the gate. And again, the reason it comes in is because you're trying to utilize 2-level atoms off resonant to pick up a phase shift. But when you have a 2-level medium, at least within the Maxwell block equations, even when you're off resonance, you can't avoid absorbing some of that light. Okay, so this is the error for this one particular protocol. If you look at other protocols, it's very similar qualitatively. The optical depth per blockade region always enters in. In real experiments, this number here is over 50%. Okay, so you try this gate, over 50% of the time you'll lose at least one of the photons. Yep. Uh-huh. Oh, right. This formula is not correct. Let's see. It should be. Sorry, it should be gamma 1d times total gamma divided by delta squared. So. So then I believe you get the correct answer.
Thank you.
Yep. Where? Oh, here? Yeah, so sorry, I gave the wrong expression. So so physically what I'm trying to do is I'm going to shine in photon B off resonance from my two-level medium. So for a single atom, I know that my phase shift is gamma 1d over delta. And then for a single atom, the amount of absorption or attenuation is gamma 1d times gamma over delta squared. So what I wrote down previously is incorrect. So then if you believe these two results, my goal to get this kind of extra minus sign or this pi phase here is that I want that the phase shift per atom times the number of atoms in this blockade region, I want that total phase shift is pi. So then that fixes the ratio of gamma 1d over delta to be 1 over the number of atoms in the blockade region. And now if I want to calculate the absorption, I should take the absorption per atom, so gamma 1d times gamma over delta squared, times the number of atoms. So that's my total attenuation through the blockade region. But now I should use the fact that delta is not an independent variable because I want to fix delta in a way to exactly get a pi phase shift. So once you have that constraint that you need to pick up a phase shift that's pi, then the loss you get only depends on the optical depth of the blockade region. Yep. So it's the number of atoms in the blockade region. Yep. Okay, so that kind of concludes the story of conventional textbook quantum optics or the Maxwell block equations. I showed you specific protocols to do important things potentially within quantum information, particular quantum memory for photons and a photon-photon entangling gate. We see that as a function of optical depth or optical depth per blockade radius, these errors tend to decrease rather slowly. And then in practice, when you try to do this thing in the lab, you're still left with massive amounts of error. Okay. So hopefully, if you believe what I said, if you believe that experiments don't really work as well as we want them to, then I hope you appreciate that we should really be thinking of out of the box ways that we can do better. Okay. And that's where this kind of spin model really comes in. Okay. So the goal, really, for the rest of the lectures, yep. Oh, sorry, what was your question? Yes. Yeah, so if you want a concrete reference, I believe the first author is Stoll and Stefan Durr. It's a group at the Max Planck Institute for Quantum Optics, and I believe it's a PRX from 2022, give or take a year. Okay. So they don't do the free space, they actually use an ensemble inside a cavity. So the details of what I'm saying are not exactly true anymore, but the spirit of what I'm saying is all, it still holds. Exactly, yeah, yeah. Right, so the same is you can't in practice take your Rydberg atom and take it to the principal quantum number of 5 million, right? So, okay, so the kind of, really the goal for the rest of the lectures is to convince, hopefully convince you that the Maxwell block equations can't be correct. That's not to say that they don't work, for most experiments in practice. So in fact, for a normal experiment, it actually works exceedingly well. That's probably why these Maxwell block equations have formed our foundation for quantum optics for 40 some years. Okay, they work well enough that that the mysteries are kind of, you can try to sweep under the rug. And at some point, we just took the Maxwell block equations to be a God-given fact. Okay, so I hopefully also, on the one hand, convince you that the spin model is, in principle, a correct framework to talk about atom-light interactions. So then, the way we'll kind of investigate this goal is to really go back to the spin model, the proper spin model, go and try to calculate some basic things and understand, are there any kind of significant differences compared to what we expect from the Maxwell block equations, right? So in practice, for the next lecture, we'll go back to the spin model, but really apply not to this kind of toy model chiral waveguide, but to the original physical system of interest, which is 3D atoms in free space. Okay, so recall that the claim was, this effective Hamiltonian. Let me just put a proportional sign. Is completely general, as long as I write it as a Green's function. Maybe plus some driving term. So when we go to free space, all we have to do is put in the correct Green's function for free space. What is that Green's function? So by definition, the Green's function is the solution to the wave equation in whatever environment you have, given a delta function source. So the definition of G is through the solution of this equation. So the curl of G. So these curls are evaluated with respect to position R. So I have R and R prime minus omega squared over C squared of G equals 3 pi C over omega delta of R minus R prime tensored with the identity matrix. Okay, so I'll explain that matrix a little bit later. But basically, you recognize the left side as the usual wave equation for electromagnetic fields in empty space. So this is like the solution of the wave equation with a point source. Okay, where the source is coming from this delta R minus R prime. Okay, there's some kind of weird coefficients here. That is a little bit arbitrary. I introduced these coefficients just to make the final form of the Hamiltonian a little bit nicer, to write it in kind of natural units. Okay, so one technical point is that G is a 3x3 matrix. So when I did the chiral waveguide, I was a little bit naive. I kind of assumed that electromagnetic waves were some kind of scalar wave. But of course, my real electromagnetic fields are vector fields. And so G is a 3x3 matrix. And particularly if I write Gij of R prime omega, the way to physically interpret this is it's the ith component of a field at position R, due to a radiating dipole of orientation J at position R prime. Okay, so physically the picture is I have a dipole at R prime. It's oscillating like e to the minus I omega t, but its dipole moment is oriented along direction J. Okay, so I and J can be X, Y, or Z. And then I'm trying to find the fields, the component of the fields at some observation point R. Okay, so it makes sense, like my dipole here can have 3 possible orientations, X, Y, and Z. And then I have to ask what are the 3 components of the field radiated at position R. Any questions on that? So in practice, we're at the end of the day, I'm going to kind of sweep under the rug all these kind of polarizations again. We're going to choose atoms with just some fixed polarization. So G turns back into a number. I just want to explain, as a bit of an aside, what we're really doing before we go and sweep everything under the rug. Right. If you want a concrete example, so let me actually write out G. So in free space, G is translationally invariant. So I could just define one of the points R prime to be 0. So you won't have to kind of remember these solutions, but the point is when I write it out, I think it'll look rather familiar to you, or at least the general spirit of it. Okay, where I define rho as a dimensionless distance. So it's r times frequency divided by speed of light. Okay. So again, the particular form doesn't really matter, but you'll notice that it contains stuff that you're familiar with. So for example, when rho is very large, so when I'm at a far distance from my source at the origin, the leading term, so there's a 1 over rho cubed here, there's a rho squared here. So the leading term is 1 over r. Okay, that reflects the far field's radiation pattern, the kind of usual lobe radiation pattern of an oscillating dipole. And then when you get very close, the leading term is actually 1 over r cubed. That's just to say that when you have a point dipole, whether it's radiating or even static, the near field of a dipole looks like 1 over r cubed. Okay, so this kind of weird object here just exactly encodes the dipole radiation pattern both in the far field and near fields that I'm sure you've seen or solved at some point within classical E&M. Yep. Yes. Yeah. Okay, so maybe this is a good stopping point for now, unless there's any more questions. No, I think that I already answered. Yeah. Okay, so in that case, I guess.
So we come back after lunch?
Yep.
Okay, great.